We are starting our math journey in ABAP with a linear algebra package. As expected, the data sciences project leans heavily on linear algebra, so it makes sense to start there. The main package is called ZCL Linear Algebra, and it starts with a single class where we will implement the operations needed to a vector object, represented by class ZCL Vector. We will implement the following methods to this class. First, the constructor, where it will take three parameters. The first is the notion of the axis of the vector, and the second a reference to an existing vector we wish to do a shallow or deep copy into the new instance of the vector class, and the last is a flag indicating whether deep of shallow copy is being requested. Most subsequent methods would take a vector as parameter to the instance of the class, or two vectors as parameters where the result will be the second vector operated upon the first, resulting in a modified first parameter and no changes done to the instance. This is in lieu of creating a series of static methods whose processes are the same as the instance ones. Recall that we cannot name the same method as instance and static, so in order to keep the class small, the optional second vector is always present. Unless otherwise mentioned, all operations would take these first two parameters, a required vector as first parameter, and the optional vector as second parameter. Second, the following operations are provided to support a generic real number vector. A. The addition operator. B. Cross product. In this first version, we are limiting the vector to a rank of 3 dimensions. In further versions, specifically after we implement the class supporting matrices, we will augment this cross product to support n dimensions. C. The dot product operator. D. The element-wise multiplication. E. The normalize operations, which performs the canonical orthogonal normalization of the vector. F. The scalar multiplication. G. The vector subtraction. H. The toString method, which returns each axis values as a pipe delimited string. And lastly, the elements methods, which return a copy to the vector axis. We now switch over to the local objects and create a function group to host our testing module. Inside this function group we create a function module that tests each portion of our code, rather than creating a test class that bloats the original code and serves no purpose once it is finished. We take the approach of a CCD and reuse our function modules in either an envelope of tests or a program call each function module independently. For the ZCL vector class, we start by creating a random axis X with type float and initialize 3 vectors with random floating numbers from 0 to 1. As we probably would perform stochastic operations on these vectors, it makes sense to keep them in a statistical realistic closed set from 0 to 1 inclusive. As such, take a look at the data definition and note that we defined 4 vectors, though only performed operations thus far with the first 3 ones. The next code block creates random floating point elements and create 3 vectors with rank 1 and length 10. From line 30 to 32 we instantiate the 3 vectors v1, v2 and v3, and we are now ready to begin testing our ZCL vector class methods. For that, we start the debugger and set a breakpoint at the first line where an instance of class random is created. After the initialization takes place, we create the random values and store them into a container to be used as parameters for the constructor of the 3 vectors. The constructors for v1, v2 and v3 are called in to create instances of ZCL vector objects. Take a close look at the pointer relative address for v1, which is set as 056. This will become important as we run the test through the series of next steps. The 3 vectors are now created and their pointer addresses shown at the right side of the screen. Let's examine the instance v1 in details, especially the abstract data type container used to store the elements of the vector. Note that we are using an internal table at the moment. Note the elements of v1. The next thing we do is to test the instance to string method, which returns a pipe delimited string with the vector elements. We will show this string later on. Now, we are calling into the scalar multiplication of vector v1, which means the size of the vector is scaled up or down. Multiplying a vector by a positive scalar will only change its magnitude, not its direction. When a vector is multiplied by a negative scalar, the direction will be reversed. Our test uses equals 0.5 as scalar, so we expect our vector to change its magnitude by 0.5. The vector normalization method is being tested now. Vector normalization is the process of transforming any vector into a unit vector. For any vector v equals x, y, z, v norm equals square root of x squared plus y squared plus z squared, which gives the length of the vector. When we normalize a vector, we actually calculate v divided by modulo v equals x divided by modulo v, y divided by modulo v, z divided by modulo v. A unit vector is a vector with a length, or magnitude, of 1 unit. When we normalize a vector, we throw away the original magnitude. But, we keep the direction. For illustration purposes, let's look again at the elements of vector v1. Recall that the pointer address of the heap where v1 is stored is 056. Compare with the toString return and note that v1's elements have changed due to the scalar addition step. We are calling the normalize method to provide us a replacement of v1 with its normalized version. As such, we should expect the pointer address at the heap to change, since v1 is already allocated at slot 056, and the logic should not attempt to replace the container since it may change in the future. At the return of the normalize method, we check that, indeed, the method created a new vector which heap addresses 059 and the elements are now the normalized vector v1. In the next video, we will continue the testing steps addressing the remainder of the methods of class ZCL vector. Once we are done with vectors, we will start the creation of a class for complex numbers and extend the vectors from R into C. The complex plane will be defined in both algebraic way and polar notation. It will be the first time we use graphs in the classes to display graphically a result of an operation. Until then, subscribe to the channel if you like to learn more about data sciences in ABAP, and click the like button.